If anyone is in the room is interested in AGN and wants to join the collaboration, please do feel free to talk to me afterwards and we can talk about that. So as a brief outline of what I want to cover today, I'm going to give a basic overview of AGN for those of you who've forgotten what they are, talk a bit about what LSST is going to do and why they're really interesting in the context of LSST and a multi-epoch survey. And then going to focus on extreme AGN variability and what we might want to be focusing our follow-up on and try and persuade you that we do need to be following these targets up. But then talk about some of the challenges and issues that we as a community are facing to go from photons sitting in the LSST camera to science coming out the other end. Okay, so I'm sure many of you have seen all of this before, but a basic reminder of what an AGN is. An AGN is an active galactic nucleus, which is powered by accretion onto a supermassive black hole. So you have, an amount of material falling onto a black hole of between sort of 1 million to 1 billion times the mass of the sun. And as material falls on through the gravitational potential, it can liberate a large amount of energy. And I think it's always fun to remember that, gravity is something like 10 times more efficient at liberating energy than stellar nucleosynthesis. So if you take all the energy, all the matter in the center of the sun that's generating luminosity by turning hydrogen into helium and instead drop it into a black hole, you'll get 10 times as much energy out of it. So this is a kind of a cartoon of what might be going on in the middle of these objects. So you've got a black hole, and around that you've got some sort of accretion disk. And it's important to say that we don't really fully understand the structure of these accretion disks. There are some models, but we also know that those models are not particularly good in some respects. And then around that, you've got so-called borderline region, where you've got these sort of clouds of gas close into the black hole, which are being illuminated by that accretion disk. And I'm going to argue today that those broad emitting regions are really good probes of that central engine and of what's going on with the accretion flow. Okay, and the other thing you need to know about AGN is that they're processes. They're not static objects, they are stochastic processes, and that means that they vary all the time. And so this is just an example on the right-hand side. This is a particularly well-studied AGN from the STORM campaign. The x-axis here is days, effectively. This is sort of 200 to 600, so 400 days across the bottom here. And these are different sort of UV optical infrared bands. And you can see that all of these light curves are flickering. So that AGN is intrinsically variable, but it's intrinsically variable on multiple timescales, right? You can see night to night, hour to hour, you've got variation, but then you've also got long-term trends over hundreds of days timescales, right? And so this is, these are complex processes. There's different things going on at different times. And so LSST is going to be great for this, right? Because you're going to have this cadence from, sort of hours difference up to 10 years, which is going to allow us to probe some of these timescales. The other thing to sort of point out is that this variability here is already could be seen as a challenge to some standard accretion disk models, because if you're the most basic kind of disk you can think of, then actually that's going to be set by the accretion rate and the outer radius. And the timescale for changes in that accretion rate to propagate down to the center is set by the viscous timescale, which is tens of thousands of years, right? And so the fact that we see variability on hours to days to weeks timescales is already telling you that there's lots of interesting stuff going on there. So continuing on this theme, right, AGN vary, all AGN vary, but actually the longer you wait, the more they vary. So this is a nice plot from Leo Sartori's paper, where on the x-axis here, you're looking at the time scale of the process you're looking at. And so going from days over here all the way up to billions of years, right? And the y-axis here is effectively the average change in magnitude, the so-called structure function that you might expect to see across the population. So the black points are data from SDSS, Stripe 82, and PTF, as it then was. So effectively, you wait a little bit of time, it varies a little bit. You wait a bit longer, it varies a bit more. You can see this trend of, as you go up to years of timescales, the typical variability, the average variability in an average object increases. So this is actually good because it means that we can start to use this kind of modeling. I should just say, you know, obviously if you wait for longer and longer, you get to galaxy mergers and so on. I'm not going to talk about that today. I'm going to focus on the accretion disk stabilities and accretion state changes. But so this is great for LSST, right? Because we have a sort of an understanding of what we might expect the baseline to be, right? And so I'm going to come back to later is the idea that, you know, what is for a 5 sigma variability event? You know, in terms of you can have a 5 sigma difference in your reference template image, great, but actually is that could still be very much expected for a typical object, right? So what I think we want to start thinking about, what does a 5 sigma variability event mean for an AGN? And so that's what these some of these individual points are up here. These are sort of the so-called changing look quasars, where we're seeing, you know, magnitudes more variability than you might expect for an object of the same luminosity and timescale. And ST is going to be probing this huge discovery space where we might expect to see rare objects that are varying by orders of magnitude more than you'd expect given the rest of the population. So this is kind of the day to 10-year time scales that I was talking about earlier. And I'd like to argue that, you know, at some level, anything in this sort of these two red regions is interesting and worth thinking about whether we should be following up. So what could those objects be? Just as some examples of what we might expect to be finding if we go and look at that parameter space. I'm going to talk a little about changing look AGN and explain what they are, or some people call them changing state AGN. The idea that actually there's changes going on in the accretion disk itself. That's obviously really interesting because it's telling you about the accretion physics and what's happening down in the inner region of the AGN. And then if we start thinking about more exotic phenomena, you know, there's been some claims in the literature of TDEs inside AGN, or possibly, you know, stellar, you know, supernovae-like events within an AGN disk. You know, at some level, anything that could happen in the ISM could happen in an AGN disk, and what would that look like? I think it's a question that LSST might be able to give us answers to. But then there's also more, you know, exotic things that we haven't yet seen, depending on who you believe. I don't think we've seen anything personally. Some people have candidates, but binary supermassive black holes, there's a poster from Angelika Kovacevic who just talked about. There's also a nice poster from Paula Sanchez-Sars where she's looking at galaxies that were previously completely inactive, no sign of an AGN at all. You see in ZTF, they switched on and now it looks like an AGN. You know, that's a rare event. We've seen one event in ZTF, but how many more of those will LSST find? How many are going to be interesting to sort of capture the birth and perhaps even death of AGN? And then there's microlensing. You could have unusual flares. You could have, you know, stellar mass black hole binaries merging within an AGN accretion disk. You know, I think your imagination is the limit, right? How exotic could it go? So there's this whole sort of potential zoo of really interesting things that we can't really explain. We don't know how many of them there are. And what I'm going to argue is that these are the objects that are worth following up. Okay. So as an example of one of these classes, right, it's the so-called changing look AGN. We have to see these. We've got a few hundred objects already. This is where, this is zooming in around the broad Balmer H alpha line, where on sort of timescales of a few years, sometimes only a few months, you see the broad Balmer line mission appearing or disappearing or significantly changing in strength. This is an example where 2009, it was a flat sort of type 2 AGN, and then we go back 6 years later and suddenly there's a broad Balmer line there. And if you remember what I said at the start, you know, the broad line region is probing the accretion physics right in the central region, right? So if you're seeing the broad lines turn on or turn off, not only is that a challenge for the basic accretion model, but it's telling you something really fundamental about what's going on in the center of AGN. Again, this is orders of magnitude faster than the viscous timescale. It's not changes in accretion rate because they just propagate down fast enough. So this has got to be something else fundamental happening in the accretion disk at a timescale that's much faster than we expect to be seeing. Just to highlight in this particular object, we had the Swift bat X-ray light curve, and you can see over a sort of similar timescale that the ultra-hard X-ray flux has gone up by a factor of 4 or 5. And so, again, is another sign pointing towards changes in the state of the accretion disk and not just obscuration. So this is great, and we can start doing this. And I'm sure some of you are thinking, oh, great, SDSS-5 is going to do all this science, right? So for those of you who don't know, SDSS-5 is now operational in both the north and the south. And in the north in particular, it's focusing on multi-epoch spectroscopy. So it's going back and re-observing many of the known AGN that have previous Sloan spectra. And in the course of doing that, it's going to find some of the rare, interesting objects. And this is one example from a recent paper from Grisha-Zaltin, where he found, so in the top spectrum, so this is broad H beta, oxygen 3, broad H alpha. The top blue is the archival SDSS spectrum from 2001. And then there happened to be another Sloan spectrum in 2016, which is actually the green one in behind. And you can see already it's dropped by a factor of maybe 2 in flux. And then when we went back with Sloan 5 later on, it was down in this red, yellow epochs down here. So the continuum flux has collapsed dramatically. The broad H beta has also kind of disappeared. And so great, we started following it up, and we got some spectrum LCO. And within a few months, literally from, I guess, a year, 2021 to 2022, it had gone back up to this sort of intermediate state. Right, and so this is, SDSS-5 is starting to resolve these temporally, these events, in the sense that if you get one spectrum per month, you can sort of track how it changes with time. But, in the year of LSST, we would hope to be finding objects like this every night at some level. So this does raise the question, could we have targeted this source from LSST? So this is a light curve from various data sets. I'll talk you through it slowly. So on the x-axis is time, is days. The top axis is giving you years, which is probably easier to think about. So the archival SDSS spectrum was taken here back in 2001, and the so-called bright state, you can see the archival photometry sort of matches. The open symbols are photometry, and the filled symbols are the spectroscopic epochs, effectively the mock photometry from the spectrum, or the synthetic photometry from the spectrum. And so then that was the second SDSS spectrum. The top coming in is the WISE light curves, and then you can see the ZTF light curve starts here, and it all looks very, very normal, and then there's this massive dip in 2021. And it was completely serendipitous that Sloan 5 happened to switch on, and this object was already a target in the target list, and we happened to get our first spectrum right at the bottom. Right, but we didn't know what this light curve looked like when we started getting these spectra. So this wasn't targeted in the sense if we had the light curve when we targeted it. It was targeted because it was an archival known object. It could easily have been the quasar next door. And if that had been the case, we would have missed this really interesting event. And so, an open question for us as an AGN community is how can we target such objects from light curves like this? And do it in a timely manner so that we're not relying on serendipity to hit the really dim state. You can also kind of see the WISE flux is starting to drop off, which is really interesting because it's telling you something about the dust structure and the overall power, and the fact that this is likely due to some sort of obscuration event that then reformed and everything carried on as normal. But that's a separate story. I'm happy to talk later more if people are interested. So to summarize, Sloan 5 is already doing a statistical sample of sort of tens of thousands of known AGN. But this is clearly not enough for multiple reasons, not least of which Sloan 5 is only funded until 2027, and so in 2 years' time it'll be finished. It's on a 2.5 meter telescope, so it's only really targeting down to 19th, 20th magnitude. We can ask, will LSST have, would we be able to target this source from LSST? You could also ask, would we be able to target this source if it was 4 magnitudes fainter at 23 rather than 19, for example? And that's where I think ESO facilities in particular foremost, and possibly WST if it happens in the future, could play a really, really important role in probing this fainter population. And there'll be talks on all of these things later in the week, and also look at Franz Bauer's poster on changes if you're interested in FORMIST. So coming back to the big picture, we've got all of these possible interesting things that might be worth following up. How do we actually identify them? How do we go from an LSST light curve or an LSST alert to a spectral target? So hopefully I don't need to persuade you too much that it's worth following these things up, and we can get a huge amount of information from the spectra. As with any extragalactic transient, you need to know what it is, where it is, and who it is. So you need a redshift to work out how far away it is. You want some sort of classification. And with an AGN transient, a classification spectrum can start to tell you whether it's maybe changes in obscuration or absorption, whether it's changes in the accretion flow, whether it's jet activity, whether it's some other transient, whether it's just microlensing, not just microlensing, whether it's microlensing, whether it's something else, right? And then that in turn, you can also get broadline strengths and continuum slopes and start to probe the accretion physics. At the same time, multi-wavelength follow-up is always interesting for AGN. AGN are inherently multi-wavelength objects. They emit across decades of frequency. If you've got things like ALMA and radio that can start probing changes in the jet physics, and the infrared is always really useful for obscuration and so on. So we want to follow these objects up, but how do we select them? And the really difficult thing for AGN is, and what all the supernova people are aware of, right, is that AGN vary all the time. And so actually a change in the photometry doesn't necessarily mean a change in the physics or an interesting change in the physics. So this is a nice example from a paper by Matthew Graham, where on the x-axis is effectively a measure of the spectral change. It's the change in the broad H beta relative to the narrow O3. You don't expect the O3 to change. So it's effectively just a measure of the broadline change. And the y-axis on the left is Y's, and on the right is Catalina optical bands, but effectively the y-axis here are changes in the photometry. And so if you've got a change in the photometry, it doesn't always mean you've got a change in the spectrum, especially a change in the broad lines, right? And so it's not just as simple as saying this object's changed by 1 magnitude, or even this object's changed by 1 magnitude over a week. You need to be thinking more carefully about, is that expected given this luminosity, given this redshift, and so on and so forth. So this kind of comes to the crux of the problem. Last thing I want to mention, LSST will clearly issue alerts for many, many more AGN than we can follow up. We know that at some level we're going to be using the LSST variability to help select AGN for luminosity functions and the wider population. So it's absolutely true to say that only a small fraction of the LSST 5 sigma alerts will be quote-unquote interesting AGN variability. And at the other extreme, perhaps maybe not all AGN variability, especially at the faint end, will actually trigger. So how do we efficiently select interesting AGN to follow up? I think it's still an open question. And you could argue that actually, if to define what's an interesting or unusual event, you have to understand what the usual events are, what you expect. Some brokers are trying to think about this. I'm not a member of LSST, so I can say without too much bias that I think LSST is maybe doing more than some of them. In particular, there's this nice paper from Paula, which is looking at using machine learning to do anomaly detection and to try and find the unusual objects amongst all the other AGN light curves. So maybe that's one way forward, but I'd be very happy to chat about other options. If people have got ideas, please do talk to me afterwards. So to wrap up, what do I want you to take away from this talk? AGN are interesting. Yes, they're a pain when you're trying to find 1A supernovae, but actually they're still interesting. LSST is going to monitor tens of millions of AGN every night, and all of them will vary at some level. But actually that's a discovery space, that's not a problem, right? That's a really rich field. And it only needs to be some small fraction of these showing unusual variability that we need to be worrying about. And that is going to include some really, really interesting astrophysics. That will benefit hugely from prompt follow-up. If you get a good spectrum at the right time, it can give you a huge insight into what's going on. But to be able to select those objects for follow-up, we need to actually figure out what we're looking for at some level. So I'll leave it there and very happy to take questions. Thank you.